Hello everybody, my name is Iman Esadi. Welcome back to my YouTube channel. Today we're going to start chapter 4 of the David Klein Organic Chemistry textbook. Now, the four main topics that this chapter covers are 1. Nomenclature of alkanes. Here we're going to learn how to name molecules. The skill of naming molecules is going to help you a lot when determining if two molecules that you're comparing with the same molecular formula are constitutional isomers or identical, in addition to just helping you become able to learn how to name molecules using the IUPAC nomenclature rules. The second topic we'll be covering in this chapter is learning how to draw Newman projections. We're gonna define what Newman projections are, and then we're gonna learn how to draw them, and this is gonna allow us to better observe pretty much the spatial arrangements of atoms in a molecule as rotation occurs about a single bond. Now, understanding Newman projections in detail is going to be the third topic for the third big topic for this chapter. Knowing how to draw Newman projections is going to allow us to now play with Newman projections, and from that get a couple of confirmations of a molecule that we can analyze. And we're going to analyze them in terms of highest and lowest energy, and we're going to discuss some of the terms and concepts that are associated with that when we get to conformational analysis. And the last topic that we're going to cover is we're going to talk about how cyclohexanes actually look like, and chair conformation being the adopted method to show this. And then we're going to discuss how substituents on a cyclohexane can take either an axial or equatorial position on this chair conformation, and how that's going to affect the energy of said conformation. Now, there's a lot of words I've said that probably don't make so much sense right now, but that's okay. I just wanted to give you an outline of our main topics for this for this chapter. We're probably going to cover the first half this session and the latter half next session, but let's go ahead and start with topic number 1, nomenclature. Now, in chemistry, every single molecule needs a unique name. We can't have two molecules with the same name. And so we have a standard method for naming molecules. This is the IUPAC nomenclature technique. All right, and there's kind of four main parts to naming. All right, the first part is what is called the root or parent chain. This is going to tell us about the overall chain length. Here we're going to identify the longest carbon chain. However many carbons back to back are bonded to each other, our longest carbon chain is going to be our root or parent chain. Now, if there's a tie between two chains of equal length, then we're going to choose the chain with the greatest number of substituents. And for rings, we always want to use cyclo as part of the chain name. Now, we're going to get into more details about what all that means when we go through these rules over again while doing an example. All right, the second part of naming is modifiers. This is going to tell us what functional groups are attached to the chain. We're technically going to worry about this later, in later chapters, since this chapter is pretty much just nomenclature of alkanes. All right, the third part that goes into naming molecules are the substituents. This is what is branching off of your main chain. And we're going to add the suffix YL to the substituent names that are part of the parent chain. And then the last part of naming is numbering locations, right? You got to tell people, all right, we know what our parent chain is, and we have substituents. Where is everything? Where are the locations? And we do that, we communicate that through numbering locations. This is going to tell us where those substituents or branches are on your parent chain. For numbering, you always start from the closest substituent. And if there's a tie, you compare locations of the next substituent. You want the first substituent to have the lowest number in terms of numbering your parent chain and the substituents. And we're going to get into that. So don't worry about that right now. All right, now, taking all these parts, all right, you can construct the molecule name. So you need a parent chain. You need your parent chain. All right, when we get to more complicated examples, you need to know what functional groups are present because those are your modifiers. All right, you need to be able to identify the substituents or branches off of your parent chain. And then we're going to be numbering your parent chain and locations for your substituents. So those are kind of the four main components of naming molecules. All right, there's also a few things that you want to keep in mind. All right, and I'm going to say these and then we're going to jump straight into a problem to demonstrate everything, okay? So don't worry. Now, the things I want you to keep in mind: always name your substituents in alphabetical order. Whenever you're writing the full name of the molecule, all right, whenever we get all these pieces, we're going to do this piece by piece. When we get all our pieces, we're going to combine it to get our full name for our molecule. Always name your substituents in alphabetical order. All right, our commas are going to separate numbers from numbers, and we're going to use dashes to separate numbers from letters. And sometimes you're going to have a complex substituent where you have to go through all the naming rules for just the substituent in addition. All right, now, some quick things also to keep in mind. All right, whenever we figure out the number of carbon atoms that make up our longest carbon chain in the molecule, all right, we're gonna determine how many carbons are in that longest chain. All right, say the longest carbon chain in a molecule has 5 carbons. All right, we're gonna go here and we're gonna find 5 carbons. Right here, this is the parent name for that longest carbon chain. So this is a really useful table for parent names for alkanes. All right, this is something you should get used to and memorize and learn. And then whenever you figure out your parent chain, cool, it's a 5 carbon chain. We said, just as an example, here's 1, 2, 3, 4. This is a 5 carbon chain. Then after we figured out this is our longest carbon chain, well, now it's time to figure out all the branches that are coming off of this parent chain. Here's our 5 carbon parent chain. It's the longest back-to-back carbon chain in this whole molecule. All right, now what about the substituents coming off of it? All right, how are we going to name these? Hold up, I want to draw something different here so it's a better example. All right, how are we going to name these substituents? Well, again, we look at each substituent. We're going to figure out how many carbons make up each substituent, every branch. Oh, there's 1 carbon here. It's just that carbon right there coming off of the parent chain. And this one right here has 1, 2 carbons coming off that parent chain. And so in order to name substituents, we come here to this second table, name of alkyl groups. All right, this first substituent had 1 carbon, so it gets the name methyl, right? Substituents have that YL we were talking about. Parent names have an ANE at the end. Substituents have a YL. All right, now this other substituent has 2 carbons, so it gets the name ethyl. All right, so those are kind of the things that we're going to do in detail with practice problems, and we're going to just jump into one right now. Here is an example problem. All right, we want to name this molecule. What is the name of this molecule? We're going to go through each of these rules for naming molecules step by step. First step, what is your longest parent chain? So you're trying to figure out here, when you're looking at this molecule, what is the longest carbon bonded to carbon chain that you can find in this molecule? Sometimes that is going to take trial and error. Okay, so you might go, you might start here, right? 1, 2, 3, 4, 5, 6, 7, 8. Oh, that carbon chain is 8 carbons long. Dang. All right, but you want to always double check and try different variations to make sure. This is going to take a bit, right? You have to do some trial and error. What if you started here? 1, 2, 3, 4, 5. Well, that red chain, it's only 5 carbons, so clearly it's not your longest carbon chain. All right, what about, let's just try one more. All right, how about if we start here? 1, 2, 3, 4, 5, 6. Look at that one. That's a little bit longer than that 5 one, but still not as long as this 8 carbon chain. So that is, in fact, our longest parent chain. It's 8 carbons long. And if we go back to our table and we find 8, the parent name for 8 carbon chain is octane. So we're going to go ahead, we're going to write that down, octane, right here. All right, we have the first piece of the puzzle. All right, your second question that you want to add is, are there any modifiers, any functional groups? The answer is going to be no in this chapter, right? Because we're starting off basic nomenclature of alkanes. So we're not going to worry about if there's an alcohol in the chain or like in the middle of the chain or an ether, how is that going to modify the name? We're not going to worry about that yet. That's in the coming chapters. So for this chapter, the answer to modifiers, any functional groups there, is probably going to be no. All right. Now we're going to move into our third part of naming, substituents. Okay, we have our main carbon chain. It's this guy in green right here. All right. Where are all the substituents? Where are all the branches of this carbon chain? So here's a branch coming off of that carbon chain, and here's another branch coming off of that carbon chain. All right, I'm gonna number them. I'm gonna call this one 1, and I'm gonna call this one 2. All right, or you know what? What's better? Let me call them by letters. This one's A and this one's B. All right, A has how many carbons? It has. Let's not do that. It has 1 and 2. This branch has 2 carbons. Okay, so we're gonna go ahead and write that down. The branch A has 2 carbons. We're going to go back to our table for branches, for substituents. Look at that. A 2-carbon branch gets the name ethyl. All right, we're going to go back here. We're going to write ethyl. All right, now this branch B has only 1 carbon coming off of the parent chain. All right, so we're going to say B has 1 carbon. We're going to go back to our table. 1 carbon substituent gets the name methyl. So we're going to go ahead and we're going to write that down. Beautiful. Okay, so we have 1, 2, and 3 all done. Now we're going to move to our last step before we begin to assemble the name. All right, here we want to number locations. All right, here's our main branch. Let me remind all of y'all. Here's our main branch, right? I just drew it twice here. Okay, here's our main branch. Now we can start numbering on here. We can start the numbering here and call that carbon 1, this next carbon 2, this next carbon 3, and so on. Or we can start our numbering on the other side and call this carbon 1, this carbon 2, 3, 4, and so on. All right. Now, which numbering is the superior numbering? All right. What we need to figure out here, all right, is, okay, should we number it this way or should we number it this way? We want the lowest numbers for those substituents. Okay, so if we start here, all right, let me do a different color. If we start here, okay, 1, 2, 3, 4 is the first number associated with a branch, so 4. And then the second number associated with a branch is 5. So for this numbering style, we encounter our first substituent at position 4 and our second substituent at position 5. All right, cool. We're going to make a note of that. Now, if we start our numbering here, 1, 2, 3, 4, we meet our first substituent at 4 and our second substituent at 5. All right. Usually with numbering, the numbering choice you pick is the one that gives you your first substituent at the lowest number. But our first substituents are tied. They're both 4s. Dang it. What about our second substituent? And then we move to looking at our second substituent. Which one of these numbering methods gives us a lower number? Dang it. Again, they're both the same. So here in this case, if you number them either direction, you're going to get a substituent at 4. All right. In the case of a tie like this, then the lowest number is going to be assigned alphabetically. Okay. What that means is this. All right. I'm going to rewrite both of these for you. All right. This one is 4 and 5. And for 4, we have our ethyl group. And for 5, we have our methyl group. All right. And in this one, we had 4 and 5 as well. But at 4, we had our methyl, and at 5, we had our ethyl, all right? So now we're going to be competing alphabetically, all right? At both position 4, all right, this one has an ethyl group, and the other one has a methyl group, all right? Which one comes first alphabetically, E or M? Obviously, E, all right? So we're going to go ahead and go with this numbering style, all right? So we're going to start 1 here and go so on and so forth. Okay, so we've chosen our numbering style. And because we've chosen our numbering style, we also want to go ahead and write that at position 4, we have an ethyl, and at position 5, we have our methyl. Cool. So now we have everything, all right? We have 4 ethyl and we have 5 methyl. We have the numbering of our substituents. We have the name of our parent chain. Now all we have to do is put it together. All right, we're going to put it together in alphabetical order. All right, so alphabetical order in terms of substituents, and then our root, our parent chain name, goes all the way at the end, guys. Okay, so going in alphabetical order, all right, ethyl is going to come before methyl because E before M, right? So we're going to write first substituent is 4-ethyl. And look at that, we separate number from name using a dash. All right, then our second substituent, right, that's what we go up next, is 5-methyl. All right, we again divide, we separate numbers from letters with dashes. That's a rule here, okay? All right, 4-ethyl, 5-methyl, that's our last substituent. So right after that, we go ahead and slap our root name, our parent chain name at the end there. And that is the name of this molecule. The name of this molecule is 4-ethyl 5-methyl octane. All right? You're going to seem like a badass knowing how to name molecules like this in front of your friends. Okay? So get good at it. Awesome. So with that being said, look at us. We now know how to name molecules. All right? And more than happy to do more practice problems if you need. Just go ahead and comment your questions or that you want more problems in general down below. But with that being said, let's just move on to our next topic. All right, next we're going to learn how to draw Newman projections. And this is going to allow us to better observe the spatial arrangement of atoms in molecules as rotation occurs about a carbon-carbon single bond. And it's really important for us to start mastering going from bond line to Newman and vice versa, being able to draw your bond line in Newman projection and being able to translate your Newman projection back into bond line. All right, so it's really good to be able to do that. Okay, so because knowing that, we can now play with Newman projections and get couple of conformations by rotating the single bond. And with the ability to draw different conformations of a molecule, you can begin to analyze and identify lowest and highest energy conformations and label them as anti-Gauss or eclipsed, and we're going to get into the definition of those 3 terms in a second. Now, for alkanes, all right, for alkanes or for non-cyclic compounds, all right, it's really good to be able to know how to convert between Newman projections and bond line. Okay, now for cyclic compounds, you need to be able to go between Newman projections and bond line, between bond line and ring conformations, and between ring conformations and Newman projections, and back and forth in any variety. And we're going to get to that later on as well. All right, so for alkanes, whenever you just have a straight carbon chain, all right, we're only going to convey those in either bond line, or we can translate them into Newman projections. But for rings, guys, you can, this is your bond line of a ring, you can convert this into a ring conformation drawing. You can do the Newman projection for this. All right, and you have to be able to go back and forth with any drawing style and be able to understand how to do that. All right, so let's get into this. Bond line and Newman projections, all right? Bond line and Newman projections. We're going to start here, all right? Newman projections, remember, they help you visualize molecules in a new way, and you're going to be able to better observe the consequences of rotation about a carbon-carbon single bond. All right, so now we're going to learn how to convert between bond line to Newman and from bond line to Newman, all right? That's the first thing that we want to learn how to do, okay? Starting from bond line structure, how can we convert it into a Newman projection, okay? Now, let's take this bond line structure right here, all right? And let's look at it this way, all right? Remember, your Newman projections are very sensitive, okay? Your Newman will look a little different depending on where you are looking at. where you are looking at it from. All right, so you're always going to be told in what direction to observe a single bond and draw the Newman projection. Okay, so that's why I'm telling you, we're looking at this bond line like this. All right, here's our eye, and we can draw it on a human being face. All right, that's me standing right there. I'm looking at it. I'm looking at it. Let me draw that better. All right, that's me. I'm looking at it. I'm smiling. I'm happy about looking at this molecule from this angle. Okay, now I'm looking at it from that direction. For this technique, all right, the carbon I am looking at, the carbon that I'm looking at, I'm going to be drawing it as a dot, okay? I'm going to just draw it as a dot really quickly, and you can see it right here. All right, and now the carbon right after it, right behind it, I'm going to draw as a big open circle like this. All right, now this isn't a very scientific way of doing this, all right, but this is the best way that I've found to be useful for people to learn this, that I've taught my students and they like. All right, I draw a circle at the carbon I'm staring at, solid circle, and then a big open circle at the carbon right after it, right behind it. Okay, so now my molecule looks like this. It's the new bond line, all right? This is what's in style now. Okay, I drawn a circle at the direct carbon I'm looking at and a big circle at the one behind it. Now, really quickly, I'm going to modify this bond line, all right, to help us a little bit. Okay, I'm going to modify this bond line. And I'm going to give this chlorine a wedge. And I'm going to give this bromine also a wedge. Alrighty, let me draw that. It's not showing up. 1 second. Oh, there we go. Alrighty. I'm going to give both of them a wedge. Now, this is a good place to stop and discuss something. Alright, whenever you see a wedge, alright, and then some sort of molecule like chlorine, a wedge means that this molecule is kind of pointing out of the page. All right, it's coming at you. It's coming out of the page. If you see a molecule drawn on a dash, all right, that means it's going into the page. Whenever you're converting bond line into Newman, all right, some of the substituents on the carbons you're looking at, whatever is going off, is going to be drawn in either a wedge or a dash to help you know if it's pointing out or into the page, because that's going to be really important when you draw your Newman, so you know where to put things. All right, so keep that in mind. Awesome. So our chlorine is on a wedge, and so is our bromine. They're both coming out of the page. All right, so we're going to modify this. All right, so once again, I'm looking at the carbon right here. That first carbon I'm going to draw as a solid dot. The carbon right after it, a circle. All right, so now what I want to do, all right, looking at this molecule from here, all right, I'm facing the chlorine on my side, all right, the chlorine is coming out of the page while I'm looking at it like this, so out of the page, all right, and there's an implied hydrogen right there. Remember, carbon forms 4 bonds, and this carbon we only see has 3 bonds, so there's a hydrogen there. If the chlorine is coming out of the page, the hydrogen is back pointing into the page. All right, they can't both be wedges, and they both can't be dashes. All right, one has to be a wedge and one has to be a dash. If the chlorine's on the wedge, that hydrogen that's there is on a dash. All right, so if my chlorine is coming out of the page, all right, and I'm looking at it straightforward on like this, all right, and it's coming out of the page, so I'm going to draw it as the right hand coming out of as this hand coming out of the page, and the hydrogen is right here. So I'm drawing myself, chlorine coming out of the page, all right, hydrogen going into the page. Now, if I'm doing that, then here is my carbon. This is the branch that's coming here, all right? That's this, just this one carbon coming off of it, I'm going to draw right here. All right, remember, where's my carbon is me, right there. I've drawn my hydrogen going into the page, my chlorine out, and this branch right here is this right here. All right, but now I want to make sure that I draw it properly with each thing on the proper side. So I'm going to go ahead and dissect this, what I've drawn here, knowing that the chlorine is going out of the page, so coming up to my right, on the left side, I'm sorry, and my hydrogen going into the page on my right side. All right, so the way that you figure this out is you draw your person looking straight at this on their side. All right, chlorine is coming out of the page, so this is their left hand going out, and the hydrogen's going into the page. This is their right hand going in. All right, so you want to make sure that you're putting these on the right side, on the proper side for them as well. All right, so your chlorine's your left hand and your hydrogen's your right hand. All right, so when we're breaking this up and we're drawing it as this piece, we have to make sure our chlorine is on the left side and our hydrogen is on the right side. All right, and then this branch is just going down. All right, so that's how we draw the first part of this, all right, with our first carbon. All right, it's a dot right here with the proper things in their place. Now, what about this back carbon? All right, well, this back carbon has this branch coming off of it. All right, and we're just going to draw that straight up because the other two groups are going to be going at the bottom here. All right, now, again, let's look at this. Let's look at this properly. All right, I'm going to move myself over here. There's my eye and my beautiful hair. Okay, so I'm looking at this. I'm sad now because this is a lot of work. My bromine is coming out of the page, so I'm going to draw it coming out of the page. All right, that's my left hand. Then there's a hydrogen there also. All right, it's going into the page, so I'm going to draw my hydrogen like this, right? Because I'm looking at it. Something's coming out of the page, and if I stick up the hand that goes out of the page while I'm on that side on that side looking that way, all right, my left hand goes out of the page, my right hand goes into the page. All right, so that's how I want to draw my bromine and my hydrogen. My hydrogen is on the right side, my bromine is on the left side. All right, and so now I have the two pieces that I need, and all I have to do is overlap the two. All right, and by overlapping the two, here's my front carbon and here's my back carbon. All right, now my front carbon has that chlorine on the left and that hydrogen on the right. All right, and since those are the two substituents that are coming out and in, all right, they're drawn pointing both up in the same direction, and this branch was going down a little bit, which is why we put it down. All right, and now when we draw the second part, this carbon in the back, all right, we had this methyl group going up, which is why we drew it up here, and then the bromine and the hydrogen down below. And the bromine was on the left, so we made sure that it was on the same left, all right, and the hydrogen on the right. All right, so that's how we're going to convert our bond line into a Newman projection, okay? We're going to draw our front carbon as a circle. We're going to draw, here, let me start this over just as a reminder. All right, we're going to draw our front carbon as a dot. All right, and we've drawn it as a dot here, okay? These two groups are at the top, so we have to make sure those two groups are drawn at the top. All right, and this branch is kind of tilting down, so we've drawn it at the bottom. All right, your Newman projections are always going to have this style, all right, where you have, you know, your front carbon and your back carbon, and if your front carbon had things going at the bottom, then your back carbon has to have its two substituents going to the top. Anyways, so we drew our front carbon and we drew the substituents appropriately. We figured out chlorine, if we're looking at it from our side and it's going out the page, we're sticking our left hand out the page, and our hydrogen's going into the page, we stick our right hand into the page. Okay, and now when we're looking at the bromine, we're doing the same procedure, and we figured out bromine's on the left and hydrogen's on the right. And we were able to convert our bond line into Newman. And don't worry, we'll do even more practice problems here to solidify that. Second thing we want to cover is going from bond line, from Newman to bond line. All right, so when we do this, when we're converting from bond line to Newman, we're going to take this first layer, all right, our front carbon's right here, look at that, and the things attached to this front carbon are these three things. So we're going to go ahead and we're going to draw them right here. All right, we're going to draw them like so. Beautiful. All right, now we're going to look at our back carbon, guys. Our back carbon is this right here, and we're going to attach our front carbon to the back carbon, like so. What things are attached to our back carbon? Well, we see these 3 groups are attached to our back carbon, so we draw them as such. And now all we want to do is, this is kind of not proper, right? But that's a helpful way to stick everything together, not professionally at first, but then we can go ahead and we can just draw it as a proper bond line structure where this is our first carbon, here's our second carbon, and then there's a chlorine right here, so that's exactly what we did. All right, and then we have a methyl going up here, and we have an ethyl going down here, so we go ahead and draw the ethyl. And our hydrogens are implied. And there you go. That is how you convert Newman to bond line. A little bit easier, I think. But let's go ahead and let's do a few examples really quickly. All right, let's do this first problem. This is A. All right, we're at A, and we're going to be looking at this molecule in this direction. Actually, what is the relationship between of the following pairs? Oops, this is not the problem I wanted to do first. Sorry. Here's the first problem I wanted to do. All right, we're trying to convert this bond line structure to Newman. All right, so, and they're telling us that we're looking at this in this direction. All right, fantastic. So what we're going to do is that first carbon we're looking at, we're going to draw as a small circle, and that back carbon as a big circle. So we're going to go ahead and do that. Small circle connected to a big circle. All right, on our first carbon right here, all right, we have a chlorine coming on a wedge. All right, and that means our hydrogen there hiding is on a dash. Okay, and on the second carbon, we also have a chlorine on a wedge, and we have a hydrogen on a dash. All right, so we're looking at it like so, at this direction. All right, so here's me again, looking at it from the side. I now have a mohawk. All right, so I'm looking at it like this. Chlorine is coming out of the page, like so. And hydrogen, ooh, where's my pen? And hydrogen's going into the page like this. Now, if you're looking at me like that, chlorine is my right hand, and hydrogen is my left hand. All right, so we have to make sure that we draw that appropriately. And they're both facing downwards, by the way, whereas this third branch coming off the carbon is slightly tilted up. All right, so we're going to draw that portion first. All right, since we figured it out. Here's our methyl group up. All right, our chlorine we said was on the right side, so here's our chlorine, and our hydrogen is on the left side. Beautiful. Now let's figure out the second piece to this. All right, and then we're going to put them together to draw our final Newman structure. So let me do a different color. Here's our second carbon. All right, we have this methyl group going down, so right away we're just going to draw this down. Now I'm looking at it still like so. I'm just going to move myself over here. All right, smiling. I have nice eyelashes. My mohawk. All right, cool. So if I'm looking at it like this, chlorine is coming out of the page, and hydrogen's going in. All right, chlorine is again my right hand, and hydrogen is my left. All right, so I have to draw my chlorine on my right side and the hydrogen on my left. Now we're going to put these two pieces together to get our final Newman structure. All right, so here we go. All right, and now I'm going to, I want to do this in different colors so you can tell between the different layers, okay? All right, so my first carbon, right, it had a methyl group here at the top. We're just going to write methyl, right, because it has just that one carbon right here. All right, we drew our chlorine on the right side, hydrogen on the left. And then for the back carbon, the second carbon, all right, we had our chlorine on the right as well, hydrogen here, and this was just another methyl group. So here is our final Newman projection. I'm going to let you do B yourself, and I'll be posting the answer. And we're going to go ahead and move into this next problem. All right, this next problem pretty much asks us to draw the Newman projection for this molecule. All right, so we're looking at it like this. So I'm going to go ahead and finish this face. All right, kind of creepy, but whatever. All right, so this is our first carbon. All right, and this is our second carbon. So let's focus on that first carbon. All right, we have that methyl group going down, so we're going to draw it down. Here's our methyl group. And we don't really have anything here besides 2 hydrogens. All right, we just have 2 hydrogens here. All right, so that means that 1 hydrogen's on the left and 1 hydrogen's on the right, and it doesn't really matter which is which because they're both the same. So we're going to go ahead and we're going to draw both our hydrogens like this. Cool, that's the first part, really easy. Now what about that back carbon? Well, this back carbon has it has this group pointing down. All right, this group has a name. It's called tert-butyl. I'm going to go ahead and draw it at the bottom here. And then what we have at top here is another tert-butyl group. All right, in the back right there. And also a hydrogen. Oh, I'm sorry. This is the let's fix this up. Let's fix this up. I'm so sorry. This tert-butyl is pointing up. Oopsie, I missed that. And then this one right here is coming out of the page, and the hydrogen that's attached to that carbon is going into the page. All right, so if I'm looking at them this way, all right, my tert-butyl is going out of the page, all right, and that's my right hand. All right, and my hydrogen's going into the page. That's my left hand. All right, so we got to draw our hydrogen on the left and our second tert-butyl group on the right. And now all we have to do is put these 2 pieces together and get our final Newman projection. So here's our first carbon, and the carbon right behind it has this tert-butyl group, this hydrogen, and this other tert-butyl group. So that's our final Newman projection. I hope this was helpful. Let me know if you have any questions at all in the comments below, or email me any problems if you want me to make additional videos with just more problems if you feel like you need them. More than happy to try and do that for you. Other than that, I hope this was helpful, and we're going to finish chapter 4, the rest of chapter 4 in the next video. Have a great day.